Hey there. I'm James Moore, and my compatriot Khalil Oppenheimer and I will be sharing how we improved HBase availability in a multi-tenant environment. There we go. So overall for this talk, I'm going to start off with who is HubSpot, who is the big data team at HubSpot, what problems we're solving, how you can reduce the cost of a region server failure, improving the stochastic load balancer, eliminating workload-driven failure, and finally reducing the impact of hardware failure. So who are we? HubSpot is an inbound marketing company that helps transition existing sales companies from outbound sales to inbound customer acquisition. Our big data team provides HBase as a service to over 50 plus product and engineering teams. And HBase is HubSpot's canonical store of customer data and has been very reliable at that. What problems we're solving? So in a typical month, we lose 3.5% of our region servers. And when you have about 160 servers in some of your larger clusters, that adds up. We have 3,500 individual microservices that talk to 350 tables. We have 500 plus terabytes of raw data in HBase, and we run an internally patched version of CDH 590. And we have 4 nines of availability in every one of our HBase clusters. So first, reducing the cost of failure. What does a region server crash look like? So first, you have detection, which in our environment takes less than 10 seconds. We have the heartbeat interval in Zookeeper tuned down very aggressively. We have then enter log splitting, which typically takes 20 to 40 seconds. And then finally, region assignment, which can be 10 to 30 seconds. This is a chart showing our actual region server crashes and how long it took to complete that log splitting performance. Overall, there's a minimum of 5 seconds that you can't get below because of the time limit on the DFS lease recovery. And it scales linearly beyond that as you add more HLogs. Going into region assignment and log replay, the process gets a little bit more interesting. This is at least a quadratic process in HLogs times regions. And in our curve fitting, it does tend to look more like an exponential curve, which we're not entirely sure why as of yet. But the important takeaway here is that the more regions you have to assign, the longer this process will be. So how do you improve the mean time to recovery in this environment? So one very simple solution that we came up with is that you go from running 8XL instances in Amazon, which are effectively mapped to controlling the entire instance or server, to 2XL instances, which means that there are 4 of those per actual server. They're still pretty beefy. You end up with 61 gigabytes of RAM instead of 244 gigabytes of RAM. But you have a lot more of them, so the impact of any individual hardware failure is smaller, about 1/4 as bad, and it also recovers much faster. This change dropped our mean time to recover from 90 seconds to about 30 seconds. And they're still pretty decent size. This also has a nice benefit to GC in that with a heap that's 1/4 the size, your pause times are going to be dramatically lower. We did run into issues along the way, though. In particular, the async process had issues with respecting the operation timeout, and metafetches also did not respect the operation timeout, which meant that you were actually continuing to retry up until the maximum retry limit. So moving on, what about stalled instances? So this is a chart that I'm sure is familiar to many of you. It depicts a region server in a normal cluster going from having really only a couple milliseconds of queue time to suddenly hundreds of milliseconds of queue time. Or in some cases, it can even be thousands, which very few applications can reliably tolerate that kind of latency difference. What kinds of causes can trigger this? So you have degraded hardware performance that involves slow I/O. One spinning disk is a spinning disk and decides that it's going to take 500 milliseconds to service a request rather than 8. You can have stuck kernel threads. It's very difficult to have software that reliably delivers when it can't guarantee that it's even running on an existing CPU. And you can have high packet loss. We run in Amazon, and every now and then we just have a bad day in the network. Finally, long GC pauses. If your application is GCing, it's not doing work. Hot regions or noisy users. With those 3,500 plus microservices, it's very easy for one batch job or worker to suddenly spike up and overwhelm the region server on a workload that otherwise had no spikes. So what's kind of our strategy to deal with these issues? Our first one is to eliminate usage-related failures. If a user is sending in a RPC with 1 million records in it as a batch put, that's probably a bad use case, and they should know about it. Then Tune GC, which our own Graham Beecher gave a great talk about this last year at HBaseCon, and there's a nice little bit.ly link if anyone wants to take a look at the blog post. Then monitor and proactively remove misbehaving hardware. So hardware doesn't just fail in a hard, like it's off the network, you'll never hear about it again. It also fails in a partial way. And if you watch dmessage or other such kernel logs, you can start to see that before it happens, and then you can queue that up for removal. So to eliminate usage failures, we keep regions less than 30 gigabytes as a hard upper limit. Our own normalizer will cut them off above that and force a split. Also, it's very important to use the normalizer to ensure that your tables have roughly even region sizes. In a multi-tenant environment, big region size differences will typically mean an uneven workload distribution. So we kept the difference between the smallest region and the largest region in a table at a factor of 4. Then optimize the balancer for multi-tenancy. Khalil will be chatting about that shortly. And then usage limits and guardrails. Improving the balancer.
Great. Thank you, James. All right, so now I'm going to talk about some of the work we've done on the balancer. So this is a journey about finding stability through balance. And let's start. So we began investigating some issues that our clusters were having, and we found a couple of issues. The first issue was that the balancer stops running when servers have the same number of regions. The second issue we found was that requests for tables were not well distributed across the cluster. So lots of requests for particular tables were just hitting subsets of region servers when we would have expected that perhaps those requests would be well distributed across the cluster for those tables. We also found that the balancer performance itself didn't scale so well with the cluster size. So I'll talk a little bit more about each of these now. But first, we're going to do a quick refresher on the stochastic load balancer, just for those of you who aren't familiar with it. So we have these generator functions or candidate generators, and the balancer starts by randomly picking one of them. Once it picks one of these generators, that generator's responsibility is to generate an action, which is either a region move or a region swap. So let's say the load generator, for instance, all it tries to do is generate region moves or swaps to make sure that region servers host the same number of regions. So that thing spits out this action into a number of cost functions. Each of those cost functions just assesses that region move or swap and outputs a value between 0 and 1 that says, is this action costly for the cluster or not so costly, based on what that cost function is trying to optimize. Each of those cost functions has an associated weight. So you weight each of those costs, and you basically sum all those up. So it's like this dot product of these costs and weights. And then you ask yourself, is the cost better or worse than before the action? If the cost of the cluster is better, then we keep the action. So if the cost goes down, we apply that action and we keep moving along. And if it's not, then we don't. So this first issue, that the balancer stops when servers host the same number of regions. Well, our theory is that this was actually just a design choice when the balancer was simpler. This is actually a configurable parameter in there. And so our solution was actually to just disable the so-called slop logic for the stochastic load balancer, which actually set some threshold about when the balancer should run based off of how well the regions were distributed among servers. And our logic here is that the stochastic load balancer's purpose, in our eyes, has evolved from just making sure that servers have the same number of regions. It's trying to optimize a bunch of other different things: locality, table skew, read requests, etc. So that was the first thing. The second thing, so requests for tables not being well distributed across the cluster. Well, our theory is that the cluster has high table skew. And you might be asking, well, what is table skew? So if you don't know, table skew is, if we look at this case here, in the balanced cluster case, you can imagine that each row here represents a server. And we can see like server 1 hosts regions R1 through R4 and regions Q1 through Q3. Server 2 here hosts regions R5 through R8 and Q4 and Q5. And the color indicates that those regions all belong to a particular table. So in the first situation, it's pretty balanced because each server hosts roughly the same number of regions from each table. Now, in the second situation, we can see that server 1 here hosts a lot of the regions, a disproportionate amount from both table 1 and table 2. And even if it wasn't like that, even if it just had a disproportionate amount from either one of those tables, the issue is that requests to any of those regions from table 1 or table 2 are going to overload that one region server while the other servers aren't doing as much work. So table skew, the problem is basically what I just said there. And so we notice that when table skew is low, meaning when the cluster is balanced, we hopefully better distribute those requests across the cluster. So if the cluster has high table skew, we'd expect to find a high table skew cost reported by the balancer and a high responsiveness to tuning that table skew weight. Instead, we dug in and we found that there's actually a low reported table skew cost and a low responsiveness to tuning that table skew weight. So we dug in some more, and we found that regions are not evenly distributed across the cluster, so table skew is present contrary to what the balancer reports. So the balancer was reporting that table skew is very low, but we dug in and found that it actually was pretty high. So this led us to kind of pose a new theory here, which is that the table skew is actually not properly computed. And so our solution was to go ahead and create a new table skew cost function and generator, candidate generator. So basically, this new table skew cost function is going to compute it computes the number of moves or swaps required to evenly distribute each table's regions. It outputs a value between 0 and 1 proportional to the number of moves required. And you can think of this as analogous to almost an edit distance between two words. If you had the words cat and caught, you only have to substitute the letter A for the letter O, so the edit distance or the number of moves or substitutions is very small. But between the words cat and dog, there's a lot of moving required. So similarly, instead of swapping letters and words, we're talking about swapping regions between servers. So the more moves or swaps you need, the higher that table skew cost is. Now, all the table skew candidate generator do is it suggests moves or swaps that reduce the number of moves or swaps needed to reach that ideal state. So essentially, it's just optimizing that table skew cost function. All right, well, so we had these theories and we wrote this code, but did it do anything? So if we look at this graph, what this indicates are 75th percentile queue times for requests. So 25% of requests were taking longer than what this graph indicates, and 75% were doing better. Now we can see a couple of kind of like peaky stuff going on in the beginning. So we're going to play a fun game of spot the deploy, which is actually right there. And so you might be wondering, if that's where we deployed all this awesome logic, then why do we have all that stuff happening after? And that's what we call the bug fix. So we wrote all this awesome logic and we did have a bug, but I don't know if you can see the units here. This is on a matter of months. So we deployed all this back out in February, and since then our 75th percentile queue times have drastically reduced, and this has been sustained. So we found a lot more stability here through this balancer fix of this table skew stuff. So that was awesome, because stability obviously is a great thing for a data store to have. So back to our investigation, the balancer not performing so well with cluster size. So our theory was perhaps that this table skew calculation was taking too long. Maybe the old code, it wasn't being too efficient with stuff. But the issue with that was that this new code we wrote, it didn't improve the performance of the balancer. So the issue here is that on our big clusters, the balancer was considering almost 20 times less region moves and swaps than on our small clusters. So after running for 30 seconds, or we even upped it to 60 seconds, our big clusters were only considering about 5,000 region moves or swaps in a single balancer run, whereas the smaller clusters were considering upwards of 100,000. So we wondered, what could that discrepancy be? And so we benchmarked these cost functions to see, well, what's eating up all the computation time? And we actually found a surprise. If you can see here, locality computation actually eats up about 95% of all the computation time of the cost functions. And so we thought that was curious. We benchmarked the generator functions too, and surprisingly, locality here actually ate up so much of the time that the other cost functions wouldn't even show up in this pie chart that I created with Google Sheets. So this led us to believe, well, first I should say actually, brief just overview of locality. I'm sure many of you know this, but it's just a measure of how close the data is to the computation. So in HBase terms, talking about how much of region's data is on its host disk. So our new theory became that the locality computation was taking too long. So we came up with a solution, which was creatively, let's just rewrite it. So we rewrote the cost function in the generator. So the old code would recompute the locality on every region on every server, which meant reading every HDFS block location of every region at every iteration of the balancer. So as balancers proposing actions, so that's every region move or swap we saw in that diagram that's being proposed. The locality computation is going through every single region on every single server and kind of comparing these localities. The new code doesn't do that. So it starts by caching all of these localities a priori. And it's also, the big thing here is that it's actually only going to incrementally update the locality cost based on the proposed region moves and swaps. So as the balancer suggests, hey, move region 1 from server 1 to server 2, locality code is just going to say, okay, how does that affect my locality cost estimate? It's not going to go ahead and iterate over all the regions and all the servers in the cluster and do all that recomputation. It's just going to incrementally update it based off of that most recent region mover swap proposal. And so, oh, and the other thing we added separately actually is we added a per rack aware locality cost function, which is relevant because so we run on AWS and there's a charge associated, a real money charge associated with inter-rack data transfer. And for us, a single rack is an availability zone within AWS. So having this cost function logically kind of associate a balancer cost with the real world cost was also pretty useful for us. And so once again, we have all these theories and we have this code, but does any of it work? And so it actually did. So all of our clusters considered 8 to 10 times more balancer actions, and the big clusters started to consider 20 times more. So those big ones that were only considering about 5,000 actions per iteration of the balancer were now considering 100,000. The locality candidate generator went from eating up about 30 seconds of the computation time to about 4 seconds of the computation time. So it got 6 times faster. The locality cost function went from about 28 seconds to 57 milliseconds. It was about 495 times faster. And so it's not just that the locality stuff is faster. It means that the rest of the balancer has so much more time to think. All those other cost functions and generators, they're trying to optimize all those other goals. Table skew, for instance, have more time to do what they're trying to do. So summarized, we made the balancer smarter about table skew, gave it more time to think with less time in locality computation, and along with all that, we get more cluster stability through that better balance. All right, I'm going to turn it back over to James.
So we're going to start talking about how do we completely eliminate that workload-driven failure. So one interesting approach to this problem, with 3,500 plus microservices and bursty Kafka workers and other associated jobs, it can be very difficult to guarantee that one service can't overwhelm a region server. So the solution we came up with was to use a semaphore on the call runner, which effectively limits the number of RPC handlers that any given service can consume on a region server. So if a Kafka worker was scaled up recently and suddenly starts slamming into region servers hosting that table, then they will just hit exponential backoffs, and other services will continue to use the region server none the wiser. We determine what user is contacting the region server via the Hadoop username, and that's how we kind of orchestrate this whole endeavor. We also have client guardrails where with 3,500 services and about 350 engineers now, it's very difficult to communicate to everyone writing every service. Are you using HBase well? Are there things that could be done better to preserve HBase's health? And so the solution we came up with was to communicate this with code. So we have internal services that receive notifications when there's an exception. And so we can actually fire that notification to the exception service as if it was a real exception without firing the exception. So whenever any of these limits is breached on a client RPC, we will throw that exception. The engineer will see it and actually see it as if there was something wrong in their application, and they will be able to dig in and find the underlying issue with stack traces and everything else. This was a huge win for solving problems such as humongous objects causing full GCs and a few other related items. And then how do you reduce the impact of hardware failure? So as we talked about earlier, there are issues that some hardware just is not created equal. And you can find out about this via the kernel log, via dmessage, and also just TCP timeouts. As it turns out, whenever a server has high packet loss, it will always have high numbers of TCP timeouts. Although the contrary statement is not clear. High TCP timeouts do not necessarily imply high packet loss. But if you make it really easy to remove region servers, then you can just eliminate all of them that have these behaviors. So if we see a single stuck thread, we will remove that server. Same with any IO errors at all, high TCP timeouts, anything. And we use an in-house orchestration tool that we wrote called Tranquility to accomplish this, which uses effectively a priority queue and just prioritizes every server, decides whether it should eliminate them, and has a concurrency limit on how many it can eliminate at a given time. Questions?
Yes, so that everybody can hear you.
Okay. I think I have two questions. You talked about the balancer. You identified that it's not functioning because of many reasons you listed. How will I identify that in my environment it is not working? I mean, or it has issues. That how did you get to the root cause?
So if I'll just repeat the question just so I'm sure I heard it right. So you're saying, how will you identify that you're having issues with the balancer in your own deployment of your cluster?
Yes.
Okay. So that was definitely a whole process, and kind of, I'm sad to say I don't think I have an easy answer for saying like, oh, the balancer isn't working in this way, like if you're seeing these things. What I will say is that it's worth digging into a little bit. Like for us, for instance, table skew turned out to be a big thing. We noticed that particular tables workloads were overloading particular subsets of region servers. And so we dug into that, and I think we used an open source tool called the Region Inspector to actually just visually kind of look at how the regions were distributed in the cluster. And we noticed like, whoa, all the regions for this table are on this server. Probably shouldn't look that way. Sadly, I wish I had a better answer for like every use case of, if this is wrong in the cluster, it means this is up with the balancer. But,
so you notice this for both reads and writes, or?
Yeah, this was pretty across the board. Yeah, bursty workloads. I mean, in particular, I think the big one was writes, but we noticed this for both. Yeah.
Thank you.
No problem.
You point, I'll go.
Oh, start here.
Could you go back to the slide with the client guardrails?
Yeah.
Now, did those settings, are those settings set per table, per use case, per workload, or is that just across your cluster in general? I mean,
This is global. So any RPC, which if you were doing a multi-get, would be the component of the multi-get that's sent to an individual region server. That's where these limits apply. And that's across all clusters, all tables, all workloads.
so it's basically just, stopping people from doing something really dumb.
Exactly. Our balancer improvements and also the normalizer improvements really help distribute the workload evenly, and then the RPC handlers prevent people from, like, say, just accidentally spamming a region server very aggressively.
We got one in the far back.
In the far back.
I just want to know, how do you communicate? Let's say there are some applications running on the cluster, and how do you communicate the best practices with the code during the runtime?
Yeah, so as I mentioned, we have internally some infrastructure that helps report exceptions to the engineers who wrote those services. In particular, we leverage Sentry. So when one of these exceptions gets fired, they'll see an email about it, and otherwise it's an unhandled exception will blow up. This slide, maybe?
Sure. Yeah. Up here.
I have a question about the balancer. We found the same problem with you guys, your problem. I want to know your cluster have how many tables, how many regions, and how many region servers. Thank you.
So to repeat the question, how many tables, how many region servers, and how many regions in our clusters? Because you saw similar issues. Yeah. So in our bigger clusters, we're talking on the scale of table-wise, like 100 to 150 tables, talking similar number of region servers, so 100 to 150 region servers. Number of regions, probably somewhere between 10 and 15,000 region servers. Or sorry, regions. Number between 10 and 15,000 regions. Yeah.
So the locality cost improvements that you mentioned, do you remember what branch they went in for HBase?
So the issue is actually currently open, but I anticipate it'll get merged in soon. I had just opened the issue about a week ago, and it's just going through some preliminary review, but the locality should be going directly into master and hopefully backported to, well, I need to talk with Cloudera people about this, but I want to see that get into CDH somehow. So I don't know if that means backporting into 1.2 or something, but it'll be in master at least, hopefully soon.
So when we fail over master, we see issues with the assignment manager taking too long to start. Do you have similar experiences? Does it impact the assignment manager's startup time when you improve the locality calculation?
Sorry, one more time?
So in our cluster, we actually see the issue that the assignment manager takes too long to start if we fail over the master, and we have our doubts that it's because of the locality calculation. Do you see similar experience that making this fix actually increases the assignment manager, decreases the assignment manager's startup time?
So the startup time in our case, I believe, is roughly similar because it still caches all those localities initially, so it still has to do that work once. But I will say that everything that happens afterwards is so much faster that, yeah, I'd have to, I can talk with you offline a bit about that, but the startup in short is still about similar time, but the rest of the computation goes a lot faster.
Did you have to change any weights? Like all those cost functions, they have a default weight value. So did you have to play with those values as well? Or you just modified the function and kept all the values at default?
Sorry, can you repeat that?
So all the cost functions in stochastic load balancer, they all have default weight values. So those are built into the code.
Yes.
So they're not exposed as parameters generally. So you have to modify them and then they take the value. So did you have to modify them as well?
Yeah, so the weights, we have those, you can modify them configurably, and we have played around with the weights. And so our issue, when we noticed the table skew stuff, the first thing we tried to do is we said, oh, there's a lot of table skew. Let's just tune up the table skew weight. So we were setting it dramatically high. We were putting it up to 100, 200, 500, 1,000, and still noticing that table skew wasn't being reduced.
So we ran into the same issue, and I bumped up the cost to 3,000. And after that, I saw, because there's another value. So my understanding is the region balancing has a cost of 500. And all other costs are lower than 500. So if you bump up the skew cost to 3,000, then it basically balances the regions for a particular table. So we get exactly same issue, and I was able to see the request was going on a particular region server.
Yep.
And this was visible in master UI. You can go to click on your table and you can see how the regions are distributed.
Yep.
And then I just bumped the cost to 3,000 and it was fine after that.
Yeah, so bumping the cost like that can solve it, but then you run the issue if it'll override these other costs that are like these technically soft constraints because they're set by a cost, like region replication is a cost, or like region servers having the same number of regions is a cost. And those are technically, they should be hard, or you think of them as hard enforcements, but they're enforced by these cost functions. So if you made table skew like 1 million, then it might override some other very important cost function is the one downside. But yeah, we did the same thing at first as well.
All right, I'm afraid I have to cut off the questions here. Thank you very much, guys.
Thank you, guys.
Thank you.